So this is the pre-lab lecture for the laboratory that says conservation of mass, I do believe, in your syllabus, and then in the lab book, I think it actually had a different name, mole ratios. But it's the same thing. What we're going to do is a chemical reaction in a test tube, and we're going to characterize the product of the chemical reaction and compare it to the reactant the way you would in any for any chemical reaction. Now, we're reacting today sodium bicarbonate with hydrochloric acid, and we'll get carbon dioxide plus water plus table salt. Now, this is a very simple reaction in the sense that we have very common chemicals involved. Sodium bicarbonate is just baking soda. You could take it out of the pantry in your kitchen. HCl is a very common laboratory acid. It's diluted to the point where it will have the reactivity of common acids even in your kitchen, and so it would be it would have the reactivity, say, of vinegar, which is an acid in your kitchen. Carbon dioxide, very familiar gas. Water, of course, is familiar, and NaCl is just common table salt. Now, although this chemical reaction is not very exotic, there's no good reason to make table salt this way. It is one that works very well and allows us to just characterize it. So if you would, I'd like you to think of it in your imagination as if it was a much more important reaction, and I've got one to tell you about. Let's suppose that you are working for a drug company, and let's suppose that that drug company has figured out how to make a drug that cures a type of cancer. And so let's put ourselves in these shoes. And what you've done at this drug company is you've taken some guy and thrown him out of an airplane and let him parachute into the wilds of the Amazon jungle, and he's talked it up with all the shaman, and they've told him what the medicinal plants are that they use, and he's gathered them up, he's brought them back to the laboratory, and what the laboratory did is through several chemical procedures, they isolated a particular compound that's active from these leaves and that is not known except to these Amazon shaman. Now, let's suppose further that the drug was fed to some laboratory rats and all the laboratory rats died. And as a consequence, the drug will not be tested on humans and cannot be used as a therapeutic. However, knowing that it has biological activity, somebody at the company has taken the chemical and has modified it, has chemically reacted it somehow, and now you've got a very good drug that's a very good cure for cancer. You're at the point with your reaction, let's suppose that the lead compound, the thing they isolated from the leaves, is actually the sodium bicarbonate. Okay? And after reacting it with HCl, the drug that gets made that can cure cancer, let's suppose it's the sodium chloride, the table salt. Okay, now you've got some very large importance tied to this reaction, and so you will characterize it like you would if you were in that situation. First thing to be aware of is that this is very precious, because you had to pay some guy to go to the jungle and get it, and it costs a lot of money. This is very cheap, okay? So what you're going to do is you're going to make this what's known as the limiting reactant or limiting reagent. You want to try to react all of it because it's so precious. You don't want to waste any of it. So what you'll do is you'll make this the excess reagent, and you'll add way more of this than you need to react all of this, so that you're sure that the most expensive one is completely used up. So this is going to be the limiting reactant. This is going to be the excess reactant. And once you've completely reacted all of it, you're going to isolate this, and that's what we'll do today. But before you get started, you also care about something else. The balanced chemical equation for the reaction you're doing tells you a very important property. It tells you how many of each molecule will react and how many molecules you'll get. And since they're only listed once, each of these molecules will, one of them will react to form one of each of the products. So what you can do is you can say, if I have a molecule of this, I will get a molecule of that. And if I have any amount of this, I can predict how much of that I have. So let's do that. You're actually going to find the number of grams of this. I'll give you a warning. What you're going to do is take a test tube with a little boiling chip in it. It's just a little rock that helps things boil smoothly. And you will put some of this in the test tube. Now what you'll do is you'll weigh the test tube beforehand, then you'll put some in, and you'll weigh the test tube after it's in, and when you subtract the two, you'll have the weight of the sodium bicarbonate. That's in your procedures. I'm just giving you a warning. Once you've got the grams of this, you can convert it into moles. Now the reason you want to convert it into moles is because the amount of this and the amount of this are related by numbers of molecules, but not by grams of molecules. And we can count molecules in units of moles. We did that last week. We went through some exercises on that. And so the moles of this, 1 mole of this will go to form 1 mole of that as well, because moles are just a way of counting molecules. And in fact, it's a very general relationship. Basically, any moles of this you use will react to form the same number of moles of this. That is, there is a 1-to-1 relationship between that reactant and that product. So like we did last week, to convert the grams of something to moles, you always divide by the molar mass. Now the molar mass of this compound can be found by looking at the periodic table and finding the molar mass of all the atoms in the compound and adding them all together. Divide by the molar mass and you will get moles of sodium bicarbonate. Since there's a 1-to-1 relationship between moles of this and moles of that, you know that you'll get the same number of moles of NaCl. So you've predicted the number of moles of NaCl. And then what you can do is convert that to grams of NaCl. And we did that last week as well. We saw that the mole to mass conversion is always multiplying by molar mass. In this case, the molar mass of NaCl. Now, why would you want to do this? Measure some grams of this and predict how many grams of that you can make. And the answer is you just want to get a leg up on what you expect to get from this chemical reaction. In our particular situation, what you want to do is to predict how many grams of this cancer-curing drug you can make, so you can tell the marketing department, and the marketing department, while you're doing the reaction and getting this stuff, can figure out how many millions of dollars they're going to make from selling that many grams of the drug. Now, in addition to that, you've got to do the experiment, of course. This is only a guess at how much you're going to make, and when you do the experiment, you're never quite sure if everything's going to go perfect, so you might not get the amount. So before I go on, I'll say that this is called the theoretical yield. That's the theoretical yield of the reaction, and when you do the actual experiment, you're going to get grams of NaCl again. But what you're actually going to do is do the reaction and then drive off the water and the CO2 by boiling it off, and have a test tube with the NaCl left behind. The melting temperature of NaCl is so high that when you heat up and boil off the CO2 in the water, you'll have NaCl left behind. And then you measure the test tube in the NaCl. You'll have to subtract off the weight of the test tube. You'll get the weight of the NaCl. So you can get the grams of NaCl by the experiment. This grams of NaCl is called the actual yield. Okay, so you get the theoretical, you'll calculate the theoretical yield, but by experiment, you'll get the actual yield. Now the reason this matters is that you might get 10 grams for your theoretical yield, but what you actually get from your experiment is only 5 grams. That means you only got half as much as you expected. Maybe something went wrong in the experiment. And so rather than making $2 million from this grams of NaCl, you've got to tell marketing that they're only going to make $1 million because you only isolated half as much as you expected, or that you could have, okay? And the way we compare the theoretical and the actual yield is by something called the percent yield, so I want you to calculate that as well. The percent yield goes this way. We will take actual yield divided by theoretical yield times 100. Okay, and maybe I'll put the equal sign on this side. That will be equal to the percent yield. All right, so here we go. So this is all separate. So our percent yield is what we'll get in the end, and in your data sheets for the laboratory, what you'll find is at the bottom of the data sheets, spaces to do all these calculations for the theoretical yield, and then what you'll do is you'll actually have a little table where you can put the actual yield and theoretical yield, divide them and everything, and get the percent yield. Okay, now experimentally, all the procedures are there. The only things to warn you about is to follow the procedures, and they'll tell you how to go about this. I think one thing to bring to your attention is that you will put sodium bicarbonate baking soda in a test tube with HCl, and you add HCl until you know it's in excess. And the way you know it's in excess in this experiment is that all the powder, this is a powder, dissolves. It's in the solution, you can't see it, and when that happens, you know you've got enough HCl. In order to get things to react, you also have to make sure these are clearly mixed. The best way to do that is to take your test tube. Sorry, don't have a test tube. I'll say this is my test tube. And it's often called spanking the test tube. You hit the bottom in such a way that it swirls and gets the solution to swirl. You will not get a good reaction if you don't mix everything in the bottom of your test tube. You'll use a Bunsen burner. I can show you how to do that if you've never used a Bunsen burner. Also, once you're all done with your whole reaction, you'll have a test tube with NaCl in it, but you want to make sure all the water's gone, okay? And the way you make sure all the water's gone is you take your test tube with your NaCl in it, and you've heated it so it's hot, and you put another test tube over the top, and if there's any water vapor coming out of this, it will condense as steam. It'll condense as a liquid, I should say, on this, and so you'll know that you need to heat this more to get rid of all the water. So you have to do a test to get rid of all the water. The last thing I'll say is, what happens if you have a percent yield that's maybe 50%? That means you got half as much as you thought you were going to get. But what happens if you get a percent yield that's over 100%, which is the maximum you can get? It always means that your actual yield doesn't just have the NaCl in it, the product, it has something else you were unaware of. In this experiment, if your percent yield goes above 100, you've always got extra water. You didn't get out all the water, and it's adding extra weight. Okay, we will be ready to go when you get here.